Um, okay, hello again for everyone. Uh, and thanks for the Ben Hodgson for a nice and interesting presentation. And also I thank the Gerard for organizing this seminar series. So my presentation is about the last mile logistics via robot assisted EV routing and the customer-centric pickup, in which we developed a two-stage Matheuristic framework. First of all, I will focus on the problem and the model, defining the problem and presenting the model, and then we will see the math heuristic framework or the solution methodology and the result. So first of all, we need to define what is the last mile parcel distribution. So the last mile parcel distribution is defined as the final stage of parcel distribution from a local hub or satellite or a micro depot or a store to the end customer. So one of the critical challenges in the last mile delivery is that conventional van-based last mile operations actually they conflict with smart city sustainability goals. So sustainability is defined by three P's. So profit, people, and planet. So in this research, actually, we are trying to address these three dimensions. So in this research, we introduce a two-echelon system combining electric vehicles, sidewalk robots, and the pickup stations to reduce the costs and emissions while considering customer preferences that I will present about it later. So, as I told you, one of the main challenges in the urban logistics is that the conventional van-based delivery, they actually create the congestion, air pollution, noise pollution, and the local emissions, which directly conflict with Vision Zero and the smart city policies. So, but at the same time, employing these all of innovative solution in last mile delivery is complicated. So its complexity here. For example, the cities they invest in electrification, micro mobility, and the shared pickup infrastructure, but planning them separately cause problems such as extra travel, wasted facilities, and uneven service quality. So for tackle these challenges, our motivation here is that in the real e-commerce platforms, we see that the customers in the order checkout, customers may choose two types of services. The first one is home delivery. So they want to deliver the parcel to their exact address or home. And the second type is self-pickup. For example, some customers may prefer to pick up their order from a nearby hub or store. So in this research, we call the type 1 customers as a robot designated customers, which they will be delivered by the robot. And the type 2 customers are called pickup designated customers, which must be assigned to the nearby pickup station. So we choose the robot here because of their low curb time, their low short-term parking, and also existing no van access zone, for example, campus where the robots they can easily navigate in these zones. And also they have a lower delivery cost, they have a lower emissions, more flexible, and the contactless delivery. So we developed the integrated system design by jointly optimizing the EV and the robot routing and facility activation and customer assignment. So from the literature perspective, actually, we built our problem here from the well-known classic problem called two-echelon VRB. In the two-echelon VRB, as you can see in the left figure, capacitated two-echelon VRB, it is first introduced by Kroenig et al. And Perboli et al. So in this two-echelon VRB, actually there is a main depot which supplies the hubs in the first echelon by using the large vehicles. And also the hubs in the second echelon, they serve the customers with smaller vehicles. So another extension to this capacitated two-echelon VRB is that we assume electric vehicles in the first echelon. So by introducing the first echelon electric vehicles, actually these electric vehicles, they have a limited battery. And by assuming electric vehicles, we also need to locate the recharging stations in the first echelon, and also we need to add a state of charge propagation. And in the literature, this is also called a two-echelon EVRP, which is introduced by Bruening et al. So again, there is another extension. So we can add another layer, which is that we can add the pickup stations to the first echelon layer. So in the two-echelon EVRP with pickup stations, so we also have the two-echelon EVRP, but we also cover some customers by the pickup station. So here our actually approach is the two-echelon robot assisted AVRP with pickup stations and customer preferences. So our approach is two-echelon multimodal system. For example, in this figure here, as you can see, there is a depot with a square, with a black square, which is the main depot. And from this depot, the electric vehicles in the first echelon, they start their trip, which is indicated by the black lines here. And these electric vehicles in the first echelon, they visit the robot hubs and the pickup stations. So the robot hubs here, we show them with pentagons, and also the triangle here shows the pickup station. So in the second echelon, the sidewalk robots, they serve the robot designated customers. So this is the robot hub with the pentagon here. So, and the striped green circles here are the customers who prefer home delivery by the robots. So the red lines shows the robot routes here, and also the pickup designated customers by green solid circles. They are assigned to these pickup stations. So this is the whole our the network or an illustrative example of our problem. So here we have some assumptions in our problem. The first assumption is that exogenous order level service designations for the robot and pickup. This means that we know the preference types 1 or 2 and the demand and the location of each customer. So we have all this information at first. So in the beginning, we have all of this information. And also we assume that the robots and the customers, they travel by a Manhattan-based distances. So as you can see in this figure, the blue and the orange lines, they represent the Manhattan-based distances. So, and also there are other assumptions. For example, there is one robot per customer for the customers who prefer home delivery service. So there is no split delivery in the second echelon for the robot routes. And also an EV could visit a robot or a pickup station at most once. Another assumption is that the hub or pickup station could be visited by multiple electric vehicles. And also we assume that the robots must return to the same hub they were dispatched from. And also there are other operational realism for the robot. For example, we consider the pedestrian travel metrics for the customers and the robots. Also, we consider robots service times, robots maximum to duration, and also fixed dispatch overhead per robot, which includes the docking, loading, and monitoring costs. And so our model's decision architecture, in summary, I could say that the first one is the facility activation. So we select which hubs and pickup stations to open, and then there is a customer assignment. So we assign the pickup designated customers to pickup stations under coverage and capacity constraints. And then in the first echelon, we have a EV routing. So we find the route of the battery limited electric vehicles that they may need recharging at charging stations. And also the last variable is the robot routes in the second echelon. So we also need to find the robot routes from hubs to serve the customers. Our objective function here is that we minimize the total system cost, which includes that EV traveling cost plus robot traveling cost, and the pickup station assignment cost and hub handling cost, and also fixed robot dispatch cost. In summary, we developed a compact, integrated, and mixed integer linear programming for this problem. So because of the limited space and the actually limited time for the presentation, it is not possible to show the details of the mathematical model. But this mathematical model is a unified model for EV routing, hub and pickup station replenishment, robot routing, and the pickup assignment with explicit coupling via aggregated parcel flow. And also there are some operational constraints that we consider in our problem, which is that EV and robot have a limited battery capacity. Maybe they are limited fleet size of robots at each hub. And also there is a limited hub accommodation capacity, pickup station capacity, and pickup station coverage range. And also there is a load capacity for each EV and robot. And also, as I mentioned, we divide the customers into two subsets. So the customer preferences are fixed in input. Some of them are robot designated and some of them are pickup designated. So to tackle this problem, especially when the problem in large instances, our solution method is two-stage Matheuristic. So this is the actually recursive, integrated meta-heuristic and the mathematical model. So in the first stage, it is meta-heuristic, the name simulated annealing plus adaptive neighborhood search. So in this stage, in the first stage, actually, we jointly build robot routes dispatch from multiple robot hubs, and also we assign the customers to the pickup stations. So for example, here in this figure, in the right side, in the first stage, actually, we solve the parallel multi-depot capacitated vehicle routing and location allocation problem. So the multi-depot capacitated vehicle routing is actually, it refers to finding the robot routes for each hub by choosing the hubs and then by finding the each robot routes. And then also we find the pickup stations, we select them, and then we assign the nearby customers to these pickup stations. In the first stage, to make it more strong, actually we added softmax adaptive selector over 12 shaking operators. Also, we developed, we designed 4 repair operators plus 18 improvement operators. There is also periodic ruin and recurrent pulse for diversification. Also, there is a simulated annealing acceptance with geometric ruling, and also there is a soft feasibility with penalties and hard cuts. So after solving this problem in the first stage of our methodology, so now by finding the robot routes and by finding the customer assignments to the pickup stations, now we know the aggregated demands or parcels in each hub and pickup stations. So by knowing the aggregated demands at these facilities, we can start the stage two of the Matheuristic, which is a two-index mixed integer linear programming. So in the stage 2, actually, we develop a mathematical model, which is exact EV routing optimizer with strengthened inequalities. So this is actually a two-index vehicle flow formulation with single commodity load flow plus arc-based energy flow, which is inspired by some works in the literature, which is strengthened by valid inequalities also from literature. And it solves on reduced delivery set from stage 1 or the aggregated demands that I mentioned. And also we use the energy aware split insertion fallback algorithm when the stage 2 solver could not find a feasible solution. And also after these 2 stages, because these 2 stages are working independently, so we also design a post local search algorithm which polishes citing and routing without calling the second stage solver again. So this post-local search actually it's the uh, checks the actually uh, solutions in in both stages, because these stages are independent. So we must also analyze and consider the solutions which could have impact on both echelons. So, and then after finding the aggregated demands of each um, robot hubs and the pickup station, now we just need to find the EV routes. So in the second stage, actually, we solve the EVRP with split deliveries over selected hubs and pickup stations. For example, here, as you can see, we know the aggregated demands or the amount of demand as each pickup station and the robot hub. So we just need to find the EV routes, the feasible EV routes and the EVs, they may visit the charging station. So for the computational performance, we designed the uh, data set, which is modified actually, which is generated based on the Schneider et al. Instances. So we generate four sets of instances, the small size instances, which includes 5 to 15 customers. The network has 5 to 15 customers, 9 hubs, and the 5 pickup stations. And for the medium size instances, it includes 6 to 36 customers, 9 hubs, and the 5 pickup stations. For the first large size instances, it includes 40 to 75 instances with 16 hubs and 9 pickup stations. And the last instance, which is the most difficult instances, is the second large size instances, including 80 to 100 customers and 25 hubs and 16 pickup stations. So first of all, we need to evaluate the performance of the operators of our two-stage math heuristic. So here we use the metric 80%, which is defined as the average percentage deviation from the best found objective when removing an operator. So totally here you can see the impact of removing each operator. For example, as I mentioned, we designed the 12 shaking operators and the 18 improvement operators. So according to this result, the most important improvement operators is this one, which is intra-hub 2-opt, the improvement operator number 6, because it has the highest 80 percentage with 2.57, which means that without this improvement operator, the solution has been worsened. So there is a degradation for the solution without this improvement operator, and also this is true for other numbers here. Um, After evaluating the performance of the operators, now we can compare the two-stage math heuristic with the mixed integer linear programming, which is solved by Gurubi within 2-hour limit. So the results here actually shows that on small size instances, the runtime of Gurubi is around 2,700 seconds, but the math heuristic was only 16 seconds. For the solution quality, when we compare the solution quality, actually there was a 0% average gap. So this means that our design, the math heuristic, was able to reach the final solution returned by the Gurubi. And the Gurubi's optimality gap was 2% for these small instances, and it's and optimality proven for 23 out of 36 instances. On the medium-sized instances, the runtime of Gurubi was 2 hours, so which was actually the limit for the execution time. So, and also the map heuristic execution time was 60 seconds or 1 minute. Uh, In terms of solution quality, we can see that Matheuristic has been actually outperformed the Gurubi by 1.32% on average. So, but this instances, the Gurubi's optimality gap was 7% with no optimality proven in the instances. And also in the first and second large size instances, the Gurubi runtime again was 2 hours on average, and the Matheuristic was 265 seconds. In terms of solution quality, also here our Matheuristic outperformed the Gurubi by 25.43% on average, and the Gurubi's optimality gap was 25% on the instances that Gurubi could find the feasible solution. But the Gurubi was not able to find a feasible solution in 65% of the large instances. After comparing the performance of a Matheuristic, comparing the performance of Matheuristic with the Gurubi, now we did some sensitivity analysis. The first analysis is related to comparing the CO2 emission under 4 scenarios. So this 4 scenarios is the different combination of using electric vehicles or ICV. ICV is the internal combustion vehicles in the first echelon. And also for the second echelon, we consider 2 types of robots, the robots with low and high emission rate. So as you can see here in this figure, in the left side, which is the combination of electric vehicles and the robots with low emission rate, we can see that total CO2 emission is the minimum, is the lowest between these 4 scenarios, which is actually anticipated, which is expected. But here the important what it matters for us is actually comparing these scenarios, and the observation here is that by replacing the electric vehicles with internal combustion vehicles, nearly it doubles total emissions. But the changes in the robot intensity have a much smaller impact. So the conclusion is that the main decarbonization leverage in the system comes from the EV tire or the first echelon. Another sensitivity analysis, we see the impact of the parameters on the total delivery cost. So we observe the impact of changing each parameter, each problem's parameter on following metrics. So these are the metrics here that we used for this sensitivity analysis. CT is defined as the total delivery cost. CEV is the EV's traveling cost, and also the remaining cost component. And also we have the metrics for the number of used resources, such as electric vehicles, robots, the number of open hubs, and pickup station. So in the first figure, in the left above, we see the impact of changing the EV load capacity. So by increasing the EV load capacity, we could say that its immediate impact is on the total cost, which the green line. So it is decreasing. And also the huge impact is on the number of the used electric vehicles, and also the EV's traveling cost. Here in the right side, we have the actually impact of the battery capacity, the electric vehicles battery capacity on the costs and the number of resources. So here again, we could see that by increasing the electric vehicle battery capacity, so it means that the EVs, they could access more facilities, including the pickup stations. So that's the reason here we see that the number of the pickup stations with a dashed pink, pink lines, we see that it is increasing, and at the same time, the total delivery cost is reducing. And the The huge impact here also by the EV battery capacity is on the assignment cost of the customer, which is also with the pink line here, which is reducing. And also it has impact on the EV traveling cost, but not as much as strong as the what we see for the EV load capacity. And also we actually see the impact of the EV consumption rate. So by higher EV consumption rate, it means that the electric vehicle, it will consume more energy in its routes. So by higher consumption rate, we see that the number of the hubs are increasing, and at the same time, there is a slight increase in the total delivery cost and the EVs traveling cost. Also, by higher robot load capacity, we see that the number of the used hubs is decreasing. So, which means that by less number of the hubs, we can again serve the customers. So that means that it will cause in less total delivery cost, which is the green line here, which is slightly reduced, and also the EV traveling cost. And again here, for the other parameters, we did the sensitivity analysis. So for the robot battery capacity, by higher robot battery capacity, we see that the number of the robots are decreasing, the number of the hubs are decreasing, which both of them lead to decreasing in the total delivery cost and also EV traveling cost. And also for the robot consumption rate, by higher robot consumption rate, it means that the robots depletes the battery more. So this means that the robots cannot access the customers more. So this is the actually result here we can see. The number of the robots and the number of the hubs, both of them are increasing. And also at the same time, the total delivery cost also increased. And also here we have the impact of the coverage range of the pickup stations, but by higher coverage range for the pickup stations, we see that the total delivery cost is reducing. The number of the pickup stations are also reducing because by less number of the pickup stations, we could cover more customers because the coverage range is higher. And at the same time, the EV traveling cost is reducing, but the assignment cost is increasing in the higher coverage range. And again, this is another sensitivity analysis on the remaining parameters. The next parameter is the hub capacity. So, but by higher hub capacity, we see that the number of the robots and the number of the hubs are converging to the minimum number, which is 2 here in the right y-axis. And also at the same time, the total delivery cost is reducing. For the maximum available robots at the hub, by having more robots that we can allow to dispatch from a hub, we can see that the number of the used robots are increasing. And at the same time, the number of the used hubs are decreasing. This means that actually the more robots are used in less number of the hubs. And at the same time, we could see the slight decrease in the total delivery cost and the EVs traveling cost, because the EVs now need to visit less number of the hubs. And
Nima, I'd just like to point you out the time. So we are almost at 4. So I think it would be, yeah.
Yeah, I will be fast, sorry.
Yeah.
So, and also for the robot served share, we could see that if all of the customers are robot designated customers, we see that the total delivery cost is the highest, and at the same time, the hubs handling cost is increasing. And also here there is a robot's maximum tool duration, which by higher maximum tool duration, we could see that the total delivery cost is reducing, and also the number of the used robots and the hubs are reducing as well. So this is the trade-off also analysis. We actually compare the battery risk index, or BRI, with the total cost. The BRI index is used for quantifying the operational energy safety, which is higher. The higher BRI is better. So we define it as a minimum of remaining battery level of AUs divided by battery capacity for all visited nodes. So, and it is the mathematical formulation here. And also here that if we want to increase the BRI, or the safety for the energy, we need to spend more money. So the total cost will be increased. And also there is another trade-off between the customer convenience index, or CCI, for quantifying the pickup convenience for pickup users. So if when it is lower, it is better. So again, here we define the CCI as a demand weighted mean assignment distance. So the trade-off analysis, we will see that by lower CCI, again, we need to actually spend more money. So the total cost will be increased, and it is the elbow shape functions here. And for the practical insights of this research, actually, we know that now EV tire actually drives the decarbonization. So switching EV to ICV nearly doubles total emissions. Robot intensity has a smaller effect, and also the trade-off shows that the cost safety trade-offs remain favorable up to a moderate safety level. And also further convenience gains, or the lower CCR, show strong diminishing returns after the first upgrade. And so the integrated planning of electric vehicles and the robots, routing, and the pickup stations could produce cost and emission savings for a multimodal delivery system, considering customer preferences and when we need to use the robots in a densely populated or congested areas. So for the future directions, for the research extensions, we can assume that the endogenous customer choice, which means that we could pricing and do incentive-driven pickup station assignments. Also, we can consider stochastic time-dependent operations and heterogeneous electric vehicles or robot fleets. Also, for the algorithmic extensions, we could develop the exact decomposition like logic-based vendors and the branch and price methods for this problem. So in a logic-based vendors framework, the master problem actually could decide the hub and pickup station activation and the customer allocation to these facilities, which after that, we will determine the aggregated parcel demands at each facility. And then the EV and the robot routings sub-problems, they solve the exact routing operations under that design and return feasibility or cost-based vendors costs, which also known as optimality or feasibility costs to master problem. And also we can develop a learning augmented operator control, which is also known as the learning heuristic framework. And also there is a deployment path, which we can use the real case study or city case pilot for a downtown or the campus or any retailer network. Thank you for your listening, and if there is a question.